Hello everyone, today we're going to be working on fundamental problem 7.5 and this problem is asking us to determine the normal force, shear force, and moment at point C. So the first thing that we're going to do is we're going to be cutting the beam right at point C since that's where it's asking us to determine all of those things. From there, we're going to be analyzing both sides of the beam to determine which side of the beam would be easier to work with. So as you guys could see, if we were to just take a look at our left side of the beam, we would be dealing with point A, which at point A, you guys could see that we have a pin support, meaning we're going to have two unknown reactions that we're going to have to solve for, and then with that loading that we have on top of the beam. And if we were to deal with the right side of the beam, as you guys could see at point B, we have a roller support, meaning we would just have one unknown reaction. And then from there, that loading that we have on top of the beam. So because of that, I'm going to be working with the right side of the beam since I would be dealing with only one unknown reaction. But before determining the value of our reaction, the first thing that I'm going to do is I'm going to be finding those concentrated forces of that loading that we have on top of our beam to then be able to solve for the value of our reactions. So what I'm going to do is I'm going to take this loading and I'm going to split it up into two parts, giving me two right triangles. So I'm going to split it up right here. So now we're going to have two triangles. We're going to have one right triangle right here. And then the second one's going to be this one on this side. Now for a right triangle, we do know how to find those concentrated forces, which is why I decided to split it into two right triangles. So first I'm going to deal with the left side of the right triangle. So to find that concentrated force, I'm going to call that, first of all, force 1. And to find our first force, what I'm going to do is, since a right triangle is half of a rectangle, we know that to find that concentrated force is like basically finding the area of a right triangle, which we know how to find that, which is 1/2. From there, we want to take the highest point of our triangle, and we know that our highest loading of our right triangle is given to us, which is of 10 kilonewtons per meter. So that's what we're going to do, 10 kilonewtons per meter. And then we're going to multiply that by the span. So we know that we have a span of 3 meters for that. So times 3 meters. From there, we would see that our meters would cancel out, giving us just our force. And our F1 has a force of 15 kilonewtons. So we know that that concentrated force has a force of 15 kilonewtons. And now as for the location on where we're going to be able to find that concentrated force, remember that our concentrated force for a right triangle is either going to be, if you're looking at it from the lowest point of our triangle, it's going to be 2/3 in. Now, if we're dealing with the highest point of our triangle, we know that it's going to be 1/3 in. So it's going to be right here, 2/3 away from our lowest point and 1/3 inwards from our highest point. So we're going to draw it somewhere around here. And we're going to call this F1. From there, to find our second concentrated force, we're going to be doing this exact same thing. So we're going to call that concentrated force F2. Once again, we're going to be multiplying that by 1/2 times the highest point of our triangle. And since we cut it right at the middle, both of them have the same highest point. So 10 kilonewtons over meters times, and then they both have a span of 3 meters. So once again, 3 meters. From there, our meters cancel out. And once again, we get a concentrated force of 15 kilonewtons. So once again, we know that for the location, it's either going to be 1/3 away from the highest point of our right triangle or 2/3 away from our lowest point of our right triangle. So that means that it's going to be somewhere around here. And that's our second concentrated force. So now that we know the value of our concentrated forces and their locations, from there we can now proceed to finding the value of our unknown reaction at B. Since we know that it's going to be a vertical reaction, we would have to now assume if it's going to be going upwards or downwards. I'm going to assume that it's going upwards, and I'm going to call it B sub y. So to solve for a reaction B sub y, what I'm going to be doing is I'm going to be taking the sum of the moments about point A. That way the reactions at point A will not be creating a moment, meaning that I would just be able to solve for my reaction B sub y. So that's what I'm going to do. We know that the sum of the moments about point A have to equal 0. So from there we have our force 1, creating a moment. Since it is to the right and going downwards, we know it's going to be creating that clockwise moment, meaning a negative moment. So we have a negative moment with a force of 15 kilonewtons. And now for the distance, we said that since our point A is on the lowest point of our right triangle, we know that from our lowest point to our force, we said it is 2/3 of the triangle. So 2/3 of 3 meters is 2 meters. So we know that distance would be 2 meters. And if you guys want, I'm just gonna quickly just include that. So we know that in a way, I'm just gonna quickly include it. We know then that from here to here, there's 2 meters, from here to here, 1 meter, 1 meter, and 2 meters. Because once again, we said that from here to the force is 1/3, so 1/3 of 3 meters is 1 meter. And then we said that from here to the force is 2/3, so 2/3 of 3 meters is 2 meters, and it goes for both ways for both of these triangles. So we have that. Now we have our second force, concentrated force, that's also acting downwards. So we know it's going to be creating that clockwise moment, meaning another negative moment, with a force of 15 kilonewtons again. And now this time for the distance, we have 3 meters here, and then from here to here, we have an additional 1 meter, so that gives us a total distance of 4 meters. And now from there, we have our reaction, B sub y. This is to the right side of our point, but this one's going upwards, so we know it's going to be creating that counterclockwise moment, meaning a positive moment. We don't know the force because that's what we're trying to determine. And as for the distance, we know that from our point A to our point B, there is a distance of 6 meters. So times 6 meters. And all of that has to equal 0. So from here, we would simply just be solving for our reaction B sub y. So we solve for B sub y, we would end up getting a value of 15 kilonewtons. And since we got a positive number, that means that it is acting upwards. Now from here, what we're going to do is now we're going to be drawing a free body diagram of the side of the beam that we're going to be working with. So once again, previously I mentioned how we were going to be dealing with the right side of the beam. So we're going to be drawing a free body diagram of the right side of the beam. So what our free body diagram is going to consist of is basically just everything right here. We're going to be drawing everything that's on this side of the cup. So As you guys can see, we're going to be drawing our beam with a span of 3 meters, our roller support with our reaction, and this loading that we have with our concentrated force right there. So we have our beam. We know that we're going to have this distributed loading going on. Now, from there, we know we already determined our concentrated force and where it's going to be. So we're going to add that as well. We know 1/3 inwards from the highest point or 2/3 inwards from our lowest point. That's going to be our 15 kilonewtons. Then from there, we have our roller support with our reaction going upwards with a value of also 15 kilonewtons. And then from there, we're just going to add some dimensions. We know that the beam, the side of the beam that we're dealing with has a span of 3 meters. And then I already want to include how far from the cut is our concentrated force. So we know that from our concentrated force to that cut, there is a span of 1 meter. Because remember, 1/3 inwards from our highest point. So from there, now we're going to go ahead and draw our cut right here. And now we're going to include in our free body diagram our shear force, normal force, and moment. And now you're going to include this based off of the sign convention. So as you guys know, since our cut is to the left side, we know that our shear force will be acting upwards. So V is our shear force. Our normal force is going to be going away from the cut or coming out of the cut. We're going to put P for our normal force, and then for our moment, we know since our cut is to the left side that it will be going clockwise. So we're going to start off with our normal force. So to determine our normal force, we're going to be taking the sum of our forces in the x direction. We know that all of that has to equal 0. And based on our free body diagram, we could see that we don't have any other forces in the x direction besides our normal force. So that's why we know that our normal force will have a value of 0 at point C. From there, we're going to be taking the sum of our forces in the y direction to solve for our shear force. Based on our sign convention, our shear force is going upwards, so that's a positive force. From there, we have our concentrated force acting downwards, so negative force of 15 kilonewtons. And then from there, we have our reaction of 15 kilonewtons. And we know that all of that has to equal 0. So simply, we would be solving for our shear force, and we get that our shear force also equals 0. And now to solve for our moment, I forgot to write the M here. To solve for our moment, we're going to be taking the sum of the moments about the cut. We're at point C, however you guys want to write it out. So we know that since we're doing it at the cut, our shear force and normal force will not be creating a moment. So the only two things that are going to be creating the moment is our two 15 kilonewton forces plus our moment. So we could see here that our moment is going clockwise. So that means that it's going to be a negative moment. From there, we have our 15 kilonewtons acting downwards. So it's also going to be creating another clockwise moment. So another negative moment with a force of 15 kilonewtons times 1 meter. That's the distance. And then from there, we have our reaction that is going upwards. So that means it's going to be creating that counterclockwise moment, as you guys could see. So positive moment of 15 kilonewtons times the distance of 3 meters. And we know that all of that has to equal 0. So from here, we would simply just be solving for our moment. So when we solve for our moment, we end up getting a value of 30 kilonewton meters. And with that, we are done with this fundamental problem. So once again, this problem was asking us to determine the normal force, shear force, and moment at point C. So the first thing we did is we drew where the cut was going to be. Then from there, we decided or we analyzed both sides of the beam, trying to see which side of the beam would be easier. From there, we found our concentrated forces. And then with finding our concentrated forces, we then proceeded to finding our reaction at B sub y. From there, we drew a free body diagram of the side of the beam that we were going to be working with. And then from there, we added our shear force, normal force, and moment based on our sign convention. And then from there, we took the sum of our forces in the x direction to solve for our normal force, the sum of the forces in our y direction to solve for our shear force, and the sum of the moments about the cut or at point C to solve for our moment. Thank you guys so much for watching this video. Please feel free to give this video a thumbs up if you found this video useful. And also please feel free to subscribe to our channel if you guys would like to see more videos like this one.